Hypersonic missiles. Just the phrase alone sounds like something out of a science fiction movie. A weapon so fast that it can travel faster than a rifle bullet, so agile that it can dodge radar tracking, and so powerful that it could change the global balance of power. But this isn't fiction anymore. Hypersonic technology has moved from the lab into reality, and the race to master it has become one of the most critical competitions between the world's major powers. In today's video, we're diving deep into what hypersonic missiles actually are, how they work, and why nations like the United States, China, and Russia are investing billions into this game-changing technology. We'll break down the science behind their incredible speeds, explain the different types of hypersonic weapons, and explore the political and strategic implications of a world where no defense system can react fast enough to stop them. Let's start with the basics. What does hypersonic even mean? The term hypersonic refers to anything that moves at speeds greater than Mach 5, that's 5 times the speed of sound, or roughly 6,100 kilometers per hour. To put that in perspective, a commercial airliner cruises at about 900 kilometers per hour. A hypersonic missile can fly at speeds nearly 7 times faster. At those velocities, the air around the missile becomes ionized, forming a plasma sheath that glows as it races through the atmosphere. It's not just fast, it's a completely different aerodynamic environment. Now, there are two main categories of hypersonic weapons: hypersonic glide vehicles HGVs, and hypersonic cruise missiles HCMIS. Hypersonic glide vehicles are typically launched into space atop a conventional rocket. Once they reach the edge of space, they detach and glide back through the atmosphere toward their target. But unlike traditional ballistic missiles, which follow predictable parabolic arcs, these glide vehicles can maneuver laterally, changing course mid-flight. That maneuverability makes them nearly impossible to track and intercept. Hypersonic cruise missiles, on the other hand, are powered throughout their flight, usually by a scramjet engine, short for supersonic combustion ramjet. These engines compress incoming air at supersonic speeds, mix it with fuel, and ignite it to generate tremendous thrust. And like rockets, they don't need to carry oxidizers, making them lighter and more efficient. But designing a scramjet that can survive and function in such extreme temperatures and pressures is one of the greatest engineering challenges of our time. The concept of hypersonic flight isn't new. Scientists began experimenting with high-speed aerodynamics back in the 1950s, during the height of the Cold War. NASA's X-15 rocket plane, for instance, flew at speeds exceeding Mach 6 way back in 1967. But for decades, materials, guidance systems, and propulsion technologies simply weren't advanced enough to make practical hypersonic weapons possible. Fast forward to the 21st century, and that's all changed. Advances in materials science, like heat-resistant ceramics and carbon-carbon composites, have made it possible for missile surfaces to withstand the intense frictional heating that occurs at hypersonic speeds. New computing systems and sensors have also enabled precision guidance in environments where the plasma sheath can block traditional radio signals. So, who's leading the hypersonic race today? Russia was the first to officially deploy a hypersonic weapon, the Avangard hypersonic glide vehicle. Capable of traveling at up to Mach 27, it can carry either conventional or nuclear warheads and reportedly maneuver through the atmosphere at unpredictable angles. Russia also fields the Kinzhal, an air-launched hypersonic missile adapted from the Iskander ballistic missile, and the Zircon, a ship-launched hypersonic cruise missile designed for naval warfare. China, meanwhile, has been testing its DFCF hypersonic glide vehicle since the mid-2010s and has made rapid progress. In 2021, a Chinese hypersonic test reportedly circled the globe before striking within a few kilometers of its target, a demonstration that shocked U.S. defense officials. China views hypersonic weapons as a way to neutralize America's aircraft carriers and other strategic assets in the Pacific. The United States, though late to the deployment stage, is catching up fast. Several programs are underway, including the AGM-183 air-launched rapid response weaponer, the hypersonic conventional strike weapon, and the hypersonic attack cruise missile. The U.S. Approach focuses on precision, integration with existing systems, and developing countermeasures because defending against hypersonics is as important as building them. That brings us to the question everyone asks: can hypersonic missiles be stopped? In theory, yes, but in practice, it's extraordinarily difficult. Traditional missile defense systems like THAAD or the Aegis interceptor rely on predicting a missile's path, then intercepting it midair. But hypersonic weapons travel too fast, fly too low, and change direction too often for these systems to react in time. Even detecting a hypersonic launch can be challenging since they may stay below radar horizons for much of their flight. To counter this, the US and its allies are developing new layers of defense. Space-based sensors that can track the heat signatures of hypersonic missiles from above the atmosphere, laser-based interceptors, and advanced artificial intelligence systems capable of real-time trajectory prediction are all in the works. The race is no longer just about offense, it is about building the next generation of defense. Let's take a closer look at how hypersonic missiles achieve such speed. It all comes down to aerodynamics and propulsion. At hypersonic velocities, the air ahead of a missile doesn't have time to move out of the way, so it compresses violently, heating up to thousands of degrees. This creates extreme thermal and structural stresses. Engineers have to design not only the propulsion system but also the missile's shape and materials to minimize drag and withstand these conditions. Scramjet engines are marvels of engineering. Unlike turbojets or rockets, they don't have moving parts. Air enters the engine at supersonic speed, gets compressed by the missile's forward motion, fuel is injected and ignited, and the expanding gases shoot out the back to produce thrust. But if anything in this delicate balance fails, if airflow slows too much or burns unevenly, the engine can't start, cutting power instantly. That's why real-world testing is so difficult. Another challenge is guidance. At Mach 5 or higher, even tiny shifts in trajectory can mean missing a target by kilometers. The plasma sheath that forms around the missile can interfere with GPS and communication signals. Modern hypersonic systems use advanced inertial navigation units, AI-assisted control algorithms, and sometimes radar or optical seekers that activate during the final approach. So why are hypersonic missiles such a big deal strategically? Because they blur the lines between conventional and nuclear warfare. A hypersonic weapon can strike with devastating precision anywhere on Earth within minutes, leaving almost no time for decision-making. That compresses what military analysts call the kill chain, the sequence of detection, tracking, decision, and response. In other words, leaders have less time to confirm whether an incoming missile is nuclear or conventional, increasing the risk of escalation and misunderstanding. Countries view hypersonics differently based on their defense priorities. Russia and China see them as tools to offset U.S. technological superiority and global presence. The U.S. sees them as part of a broader deterrence strategy, maintaining the ability to respond rapidly and precisely to threats anywhere in the world. Beyond military use, hypersonic technology also has potential civilian applications. NASA and commercial aerospace companies are exploring hypersonic passenger travel, which could one day make a trip from New York to London last just 90 minutes. However, the engineering, safety, and environmental challenges remain immense. Now, let's talk about the costs. Developing hypersonic weapons isn't cheap. Programs often cost billions, with individual missiles priced in the tens of millions. Testing requires specialized wind tunnels, advanced materials, and high-altitude ranges. For many nations, hypersonics are as much about prestige and deterrence as practical battlefield use. Despite the excitement, experts warn that hypersonic weapons aren't magic bullets. They face significant operational hurdles, including limited production scalability, heat shielding degradation, and difficulties in mass deployment. Moreover, once every major power develops them, the deterrent balance simply resets, much like nuclear weapons did during the Cold War. Disclaimer: this video is for educational and informational purposes only. It does not endorse or promote the use of any military technology for harm. All discussions are based on publicly available information and should not be interpreted as defense advice or advocacy.